Howdy crew! In this video we're going to discuss what's called a Riemann sum. Now Riemann sums are used to approximate the areas underneath a curve, meaning we're measuring from the curve down to the x-axis. Now in this lesson we're going to do a quick review of what summation or sigma notation looks like. You looked at it back in Algebra 2 and Pre-Calc, so a quick review of that. And we're going to talk about how rectangles can be used to approximate areas, and why we typically use a right-hand approximation instead of a left-hand approximation. We did both during a lab prior to this lesson, but I want to make sure that we know why a right-hand approximation is usually a little bit easier for us to handle, along with some examples. So first we're going to talk about what the summation notation looks like. First things first is you're going to see that Greek letter sigma. Sigma just means you're going to add stuff up. And there are times where you're going to see it written horizontally like this, or you can see it written more vertically with this I and N on the top of the sigma instead of on the side. I want to start with this I. This I is called an index, and it's telling us where we're going to start our sum. So for example, this I equals 1 is telling us we are going to start with the first item. Whatever we're going to be doing with it, we're going to start with the first one, because it says I equals 1. Now this n is the number of terms we're going to have. So for example, if this n is a 6, that's telling us there's going to be 6 terms when we're all done adding. Now this f inside of here, that f is telling us what are we going to be doing? What are we going to be doing? Are we going to be multiplying numbers together? Do we have some sort of linear thing where stuff is going to be added or subtracted? Are we going to have to square some numbers, whatever it turns out to be? This function is going to tell us what to do with it. So for example, if I ask you to compute the following, if I ask you to compute starting with I equals 1 and going to 4. Now this 4 is telling us there's going to be 4 terms that are going to end up being added up. This I equals 1 is telling us to start with 1. Now if you notice this squared bit, that squared is telling us to take that index number and square it. Now for the second term, I'm going to take my index number 2 and square that. Third one, I'm going to be squaring that as well. And the last one, same deal. Now since we're dealing with a summation, our job is to figure out which each of these pieces is and add them up. So of course you probably want to turn these into nice numbers so they can be dealt with easily before you go and add them. 1 plus 4 is 5, plus 9 is 14, plus 16 is 30. Once you got the numbers, just a matter of adding them up. Now how does this apply to approximating areas? Back in elementary school or even in geometry, when you were calculating area, you had a region that was bounded by something nice. Maybe a semicircle, maybe a straight line, whatever it is. But if you notice, f of x is this curved graph. So this area from the curved graph between my bounds, between a and b, and the x-axis, this is inconsistent. So it's going to be more difficult to find the area of that blue region. So the process we're going to follow is creating a whole bunch of these rectangles. Once I have a whole bunch of these rectangles, if I know each one of their areas, and I add them all up, I'll eventually get a pretty close approximation for the area of the whole thing. Now in this picture, I'm able to know some pieces of information about each rectangle. Now to start with, the width of each one. We call the width of each rectangle delta x. Now this delta x, we know a little bit more information than that as well. Of course, it's the width of the rectangle, but we can find it. Take a look here. My blue region goes from A to B. It spans from A to B. That distance is just those two numbers subtracted. So if I take B minus A, I get the distance of the entire blue region. Now if I divide that number by however many rectangles we have, remember the n is the number of rectangles that we have, if I divide that b minus a by the number of rectangles I have, I'll find out how wide each one actually is. Now that's the width of each one. The height of each one is actually going to change from rectangle to rectangle. But what's nice here is this distance is just whatever the function is. It's measuring from the x-axis up to the blue line. It's literally just what the function is. So the height is the function. Now here's the thing though. Each height is different, so I can't just call it f of x. I need to call it f of x sub I. This sub I is telling us which rectangle are we dealing with. This I is going to be filled in with certain numbers, telling us which rectangle in my stack we're actually talking about. So here's what we're going to be doing. If we're taking a right-hand approximation, what we're going to be doing is we're going to be taking a whole bunch of rectangles, however many of them there are, and we're going to end up multiplying the height of each one times the width of each one. Delta x is the width, the function is the height. You multiply those together, you get the area. That's the area of rectangle 1. And if I keep doing that for however many rectangles I have, and then I add them up, I get the area of the whole thing. So in my sigma notation, my n is the number of rectangles, the delta x is the width, and the f of x sub I is the height of each one, all added up. Now you might be thinking, why are we focusing so much on the right-hand approximation? Couldn't we use a left-hand approximation? And the answer is yes, we could. But if you notice, it gets a little funky with your notation. Inside of my f function here, I get this x sub I minus 1. Because when you're starting with a left-hand approximation, you really have to start at the very beginning. This x sub 0 is the beginning. That very left side of the first rectangle, which makes things tricky. You actually have to take one step back instead of just starting where you would like to start. So typically we'll use a right-hand approximation so that we don't have that stepping back one, and I'll show you what that looks like in class. And using a right-hand approximation gets rid of that. But left-hand approximations absolutely can be done, and you're going to be expected to do them as well. So now let's do it. Use both a left-hand and a right-hand approximation to approximate the area under the curve of this function x squared on the interval 0 to 2. And use n equals 4. So we're going to make 4 rectangles. So what we're going to end up doing is first we need a delta x. Delta x, remember, is the width of the rectangle. So how we're going to find it? We're spanning from 0 to 2. So I'm going to take those two numbers and subtract them. And I'm going to divide by the number of rectangles I have. I have 4 rectangles spanning from 2 to 0, and I end up with a delta x of 0.5. Pretty easy. Now what I need to do is I need to find the height of each rectangle. If I'm using a left-hand one, notice that this first rectangle really doesn't exist. The reason why it doesn't exist, I'm going to put that red dot here at x equals 0. On the left side of my rectangle, there's no height there. My function is equal to 0 there, so the height of my first rectangle is 0. I still should write it in. I have 4 blanks here for the 4 rectangles. My height of my first rectangle is 0 times my width. For the second rectangle, I need to figure out what my function evaluated at 0.5 is. Now where am I getting the 0.5 from? On the left-hand side of the rectangle, I'm dealing with this x value. That x value is determining how high my rectangle actually is. And I'm going to multiply that by the width. The width of the rectangle is a half. The next one, I'm dealing with x equals 1. So the height of the rectangle is just the function evaluated at 1 times the width of the rectangle. And the last one is the height at 1.5 times 0.5. Now, of course, let me put that f of 0 in there just to make life easier. Now, of course, you're going to want to evaluate what this f of 0 is, to keep it in number form. So to do that, we're dealing with the function x squared. So we're really going to take our x value and square it before we multiply times that 0.5. So plus 0.5 squared times 0.5 plus 1 squared times 0.5 plus 1.5 squared times 0.5. And if you can simplify any of these out, it's absolutely going to be helpful to you. This first term is going to go away because we're multiplying by 0. 0.5 squared times 0.5. It's definitely worth getting my calculator out for this one. 0.5 squared times 0.5 is 0.125. I get my 0.125. 1 squared is 1 times 0.5 is 0.5. And the last one, changing that 0.5 to a 1.5, is a 1.25. Now, last step, once you've got them all done, you found the areas of each one, you just want to add them up. So 1.25 plus 0.5 is 1.75, plus 0.125 is 1.825. And again, that is the approximate area of this region shaded in that teal color. Now, if I ask you to do a right-hand approximation, the process is more or less the same. My delta x is exactly the same thing. Still going to be 0.5. Just the difference is we're going to be looking in a different place. So for this first rectangle, we're really looking at the function evaluated at 0.5 times my width. For the second one, we're looking at the function evaluated at 1 before you multiply by the width. The third rectangle is where you're starting at the x value of 1.5. That's this one. Times your 0.5, that width. And the last rectangle is your function evaluated at 2 times your 0.5. Now again, for each one of these, this f of 0.5 is really taking your x value and squaring it. So more or less is going to be what you had for the first one. That 0.125 plus 0.5 plus 1.25. And this last one, 2 squared is 4 times a half is 2. Before you go and add them all up. So I have 3.25, 3.75, 3.825 when you add them all up. Now if you notice, these values are quite far apart. They're off by 2 units. How is that possible? Well, if you notice, there's these white gaps pretty much everywhere underneath that curve. And in this one, there's a whole bunch of teal color above the line. So that's accounting for area that really shouldn't be there. In our next lesson, we're going to be talking about how to minimize that as much as possible. So some conclusions here. To create a Riemann sum, you're really going to need a function. That was our f of x sub I. A number of rectangles. That was n. And a delta x. Figuring out how wide each rectangle is. Find the area of each rectangle and add them all up. You're going to want to determine if your approximation is an overestimate or an underestimate. That should be pretty easy to see from a picture. This one was an overestimate because all of our rectangles went over the line, where the other ones were underneath the line. And we're going to experiment with that in class. Nice job.